So what we've seen is the way that regardless of what the underlying population distribution is, when we take samples and we look at the sample mean distribution, that distribution is always normal or always approximately normal. So these are the propositions that we had. Okay, so if we take random samples from a normal population, whatever the size of that population, the distribution of sample means follows a normal distribution. And we've seen that if we take samples from a non-normal population, the distribution of means is approximately normal. And we saw that that approximation sort of issue really disappears as soon as we've got samples of around 30. So, you know, that I don't want to be really fixated on saying, oh, there's a hard cutoff point for when we know that this thing bites and say that that's 30. But as you increasingly work with data, you just know that more data, this theorem really does start to bite. And the third proposition that we saw was that the distribution of sample means is much smaller than the distribution for the population as a whole. So I've called the title of this slide, The Importance of Beer. So if you've come across a t-test before, you'll know of this distribution being called a student's distribution. Okay, so who is a student? So you may or may not be aware that a student is the pen name for William Steely Gossett. Who was this person? He was the brewer at Guinness. So if you go through all the records, there's actually documentation of the minutes of a board meeting where he was the experimental apprentice brewer at the time, and he was trying to control the ferment, and it was a problem of if the alcohol content was not high enough, people would buy other beer, and because the tax was levied on the alcohol content, if they brewed the beer too high in the alcohol content, the tax they had to pay for the government was high, and so the company's, or in this case Guinness's, profit was low. So really, when we talk about applications of all of these statistical tests, this property here of the relationship between the population standard deviation and the distribution of sample mean standard deviation was really derived by someone who had actually a real world problem to solve, and that was how to make as much profit from selling beer as you can make. And so we are in debt to the Guinness company for all of these statistics that we are learning. So a real recap on what we're doing here. So we know the shape of the distribution of sample means. This thing is always normal, all right, as long as our sample size is reasonable. When we have a statistic such as the sample mean, we have a special name for calling the standard deviation of the distribution. Okay, and it's a sampling distribution, and we call the standard deviation of a sampling distribution the standard error. So the metric that we use to summarize the distribution of the sample mean is the standard error of the mean, or most people just say standard error, but when you're looking at, because it generalizes to many other cases, but in this specific case it's the standard error of the mean. So we're going to just follow through now, and we're going to see the mapping of the steps that we have to follow when we're looking at going from a sample to the distribution of the sample mean. So the final thing I want to cover is putting all these things together. So I've got just some examples that I'm going to work through with you here. So what do we do here? I have some data. I have a sample of data. From that data, I get my sample mean and my estimate of the sample standard deviation, and I say that that's my guess about what the population shape is. So I've got my sample, I've got my guess about the population parameters, and then from my population parameters, I use that property about the relationship between the standard deviation of the population and the standard deviation of the sample mean distribution, so divided through by the square root of n, to get my estimate of the standard deviation, or we say the standard error of the mean, or just the standard error, which we use for our testing. So we go step 1, I have a sample. From the sample, I use those values to give me an estimate of the population, and from the population, I can then map down to the sample mean distribution, which is what we use for testing. So let's just keep grabbing some other examples. So here's our next example. Okay, we go again, like looking at our shape in here. okay, is this a normal distribution looking in our sample data? Maybe, maybe not. Like there's quite a long tail going out here, so we probably might not be super confident in that, but it doesn't matter. We say, okay, we take our sample data, we get from the sample, we say that's our guess of what the population shape is, and from the population shape, we can then map down to our distribution of sample means. All right, let's have a look at another one. So we've just got different ones. Here again, we've got very widely spread. We take out our sample. So we go out, we get a sample. From the sample, we calculate the mean and the standard deviation. We use those as our guess for the population mean and the population standard deviation. And from that guess, we use our rule to map down to the standard error of the mean. Got a couple of others here. I think this one's clearly looking non-normal. So again, what we've got here, some data, our sample, very, very likely to be quite skewed. We don't worry about the skew. So we're going to say, yeah, my data doesn't look normal, doesn't matter. I still have a guess for the mean, a guess for the standard deviation. We know the formulas for those. That's my guess of the population. And then from that, I map down to my distribution of the sample mean, which we know is always going to hold. I've got the last one here again, maybe not normal, again like some stuff going out here in the tail. Same deal. You get some data. Your data is not the population, it's a sample. Your data may or may not look normal. As long as we've got a reasonable sample size, we're not worried about that. We take our sample, and from our sample we use this mapping rule. Yes, we guess to the population, and then from that one sample we can map down to the distribution of sample means. So remember, this distribution of sample means is something that would be there if we took many samples. We only take one sample, so we go through this sort of mental gymnastics from our one sample to the shape of the distribution of the sample mean. And that's one of the key tricks that we need to just remember in the background. Yes, data, guess the population. From the population, distribution of sample means. The sample data may not be normal, but the distribution of sample means will always be normal. And that's what I wanted to cover. Thank you.